Japan. Two contrasting oceanic plates of the Pacific Plate, old, cold, and steeply dipping, along the northern Japan, and the Philippe Sea Plate, young, hot, and gently dipping, along the southern Japan are subducting beneath the Okhotsk, North American, and Eurasian plates, respectively. Figure 4. Subduction of the Pacific Plate is at a rate of 9 cm/year with almost orthogonal angle to the trench. The Japan Trench is one of the well-known examples of tectonically erosive margin, for example. Index map of the Japan margin. Series of Forearc basins are developed between volcanic fronts and trenches. Blue lines with labels A and B indicate locations of survey lines shown in Figure 5. Plate names: PA Pacific, PS, Philippine Sea, OK, Okhotsk, NA, North American, EU Eurasian plates. Red arrows indicate the direction and velocity of plate motion relative to the Okhotsk or Eurasian plate based on ref. In the southwestern Japan margin, the Philippine Sea Plate subducts at a rate of 5 to 7 cm/year with moderate obliquity at present. In this margin, the subducting plate changed from the Pacific to the Philippine Sea Plate as a migration of a triple junction. Thick accretionary wedge, the Shimanto complex, and segmented Forearc basins have been built from Cretaceous to present between the volcanic front and the Nankai Trough, for example. Inshu and Kumano Forearc basins have been developed along the landward side of prominent outer arc highs associated with regional megasplay faults along the Nankai Trough, Figure 5. Huge amounts of studies about the basins in terms of seismic interpretations, for example, and sediment cores obtained from IAP expeditions, for example, and references therein. Interpretations of seismic profiles across A. the Inshu and B. the Kumano basins, modified from ref. Seaward margins of the basins are characterized by landward tilting strata resulted from uplift of the outer arc highs. Abbreviations: NF, normal faults, SF, splay faults, WBSF, wedge boundary strike slip fault. Locations of the profiles are shown in Figure 4. The Kumano Forearc basin of the 3 km sediments has been evolved by combined influences of frontal accretion and megasplay faults, out-of-sequence thrusts. A brief history about the basin can be summarized. 1. Small trench slope basins developed during 6 to 2 Ma on older consolidated interaccretionary wedge of the Miocene-Pliocene, Units 1 and 2 in Figure 5. 2. Splay fault development caused by a shallowing of the decollement, 2 to 1.3 Ma, uplifted the slope basins and merged them into one large Forearc basins, Unit 3. The basin floor was draped by submarine fan turbidities derived from gravity flows through submarine canyons. 3. Diachronous depositional surfaces were formed by spatial and temporal variations of the fault system around the basin during 1.3 to 0.9 Ma, Unit 4. Hemipelagic sediments were derived from the outer arc high in the seaward side of the basin, while terrigenous sediments were deposited in the landward side. 4. Continuous uplift of the outer arc high by the splay faults resulted in a stable environment as the Deposition migrated landward, Unit 5 of